Kia ora everyone, thanks for tuning into our lunchtime webinar today with the Timber Design Society. We'll just give it another minute for more attendees to hop on and then we'll get started. Just for those who have just hopped on, we're just waiting for a few more attendees to come through and then we'll hand it over to our host for the session. But to kick us off, just a little bit of housekeeping. So on the bottom of your screen, there is a Q&A button. You can submit your questions on here at any time during the presentation, but we'll collate them to the very end to spark a conversation with our speaker. Questions are also open for all attendees to view, so we do encourage you to use the upvote function on any questions that you're curious about too. And this webinar is also being recorded today and will be available on the TDS website in the very near future. With that, we're at 12:01, so I'm going to hand over to Daniel to get us started. Over to you, Daniel.
Good afternoon, everyone. Thank you, Caitlin, for the introduction, for hosting us today. So welcome to this TDS webinar. It's today about the NHERI TallWood Project. And before I introduce our speaker, Shiling and the actual presentation, just a little bit about myself. I am the past president of the Timber Design Society and am hosting together with my colleague Emma the TDS webinars, which occur every Thursday, the third Thursday of the month. Timber Design Society is always pleased to help sharing the knowledge when it comes to timber. And that's just one of the many ways of how we get in touch and discuss latest research and case study projects with all of you. The upcoming webinars, the next one is on the 15th of August, is about carbon emissions in structured timber products, the full story by Phoebe Moses from Becker. And we have a special edition of the TDS webinars on the 29th of August from Adam Jones from CLT Toolbox. And he will introduce the recently launched modules, 3 modules for all New Zealand engineers to design large dowel fasteners, big bolts and dowels to the new standard, the NSF AS 7020.1, together with brittle failure modes. And the last one, which is planned as of for now, is the 19th of September, where Paul Horn talks about mass timber structural systems and considerations during concept designs. If there's any topic of interest or if you would like to share your knowledge, just let us know, please. We're always looking for interesting topics and speakers. In terms of other news, the TDS is organizing a roadshow the second last weeks of September with more details to come. And we talk about or introduce the design to the new timber design standard, again, NZS AS 7020.1, or the novelties of that new standard coming in. Thanks, obviously, to all of you for joining, but also TDS committee for supporting these webinars and also our sponsors, FutureBuild, MyTech, Simpson Strong Tie, Ixlam, iBuild, and Rotoblast. Thank you very much to all of them. So back to the actual presentation. So the NHERI TallWood Project, you might have heard about it. And if you were in Christchurch a few weeks ago, there was a CSOC local event in Christchurch where Shiling presented. We wanted to have this presentation accessible to the wider audience in New Zealand and beyond. And although Shiling is now in Japan, he still has given us the time to repeat the presentation for all of you. So Shiling, he's an associate professor at the Colorado School of Mines, and he's also a professional engineer in the state of California. His research focus are traditional and innovative timber systems, and obviously more on that today, performance-based engineering, structural dynamics, and large-scale testing, and you will see a lot of those testing in videos today. He's also the lead principal investigator of the NHERI TallWood projects, where he and his colleagues worked on validifying design, a concept and system for tall wood projects, which are essentially earthquake-proof. And with that, Shiling, over to you. I'm looking forward to listen to your presentation and hopefully everyone gets something out of that. Thank you very much.
Thank you, Daniel. Sorry if I missed you about a month ago when I was in Christchurch. Hopefully this will provide you some information about the TallWood test we just did. So without further ado, I will get started. I will actually kill my own video because the bandwidth. And yeah, you don't need to see my face, so you're not missing much. All right, so this is apparently not something that I can do by myself. You see a lot of collaborators here, and more importantly, our graduate students who actually do all the work. So, oh yeah, really an honor to speak to the New Zealand group. And later you will know why, because in fact, the key component of the NHERI TallWood project, the post-tension, the mass timber rocking wall, is born, right there where Daniel works at TDI and Christchurch and UC Canterbury. So the real project is called Developing a Resilience-Based Seismic Design Methodology for Tall Wood Buildings. But why resilience, right? Like I said, it was based on a lot of existing work done by New Zealand experts, including like Andy Buchanan. I mean, yeah, there's more that I haven't listed here. Alexandro, Massimo, Stefano. A lot of people are working at PTL. But why are we looking at resilience? When I'm presenting at somewhere else, I say, oh, this is Christchurch, but everybody knows here. I think so. The Christchurch earthquake, and then with the modern technology, especially for Google Street View, you can actually do a before and after shot of the earthquake. So you notice something, right? This is one of the street corners. That by Hartley Park? I don't know. Yeah, you see another thing, and then this is another view of how the face of the city has changed. Another view. So you notice a lot of more, green park area and the parking space, which is good, but at the same time, a lot of buildings are gone. And also up to today, I mean, I know it's not for engineering reasons, but for more of a policy reason, but the cathedral is still being reconstructed, haven't finished after 13 years. So although if you look at the casualty of the Christchurch earthquake, there's like one major collapse of the building, which accounted for most of the casualty. And then other buildings, the buildings are, you can say, dead because they have to be demolished. But the people came out alive. So you can view this as a contrast of number, as a good thing that our design code is doing what it's supposed to do, keeping people safe. But wouldn't it be nice to do this? So that is what we're trying to do. In fact, it is funny. I'm now in Japan. I believe Japanese code is actually already trying to do this, using a different approach. I mean, Japanese code. The basically you have oversized members looking for elastic performance, but could we utilize ductility and still do this? And then if you want to look at something that move around, it's a tall structure that can survive in high seismic region for like hundreds of years, maybe wood is not a bad choice. I mean, yeah, you can build buildings out of concrete and steel, but there's a natural example here. This is actually my family in Sequoia National Park in California. It's those big redwoods those are gorgeous. But in fact, there are 3 good engineering reasons to do it with wood. At least in the United States, we have come a long way through analytical modeling and experimental testing. We gain more knowledge, compared to when Northridge earthquake happens. We know more about how to design wood, how they perform in earthquake than any time in the past, in our history. Then there is the mass timber movement. I know, like in New Zealand, although the timber research is actually quite ahead, but the implementation of mass timber is not as I would say not as prevalent as the US. Look at this figure. This figure is from actually last year. You already have about 2,000 projects that's been built or under planning. And if you look at what's been built, it's over 1,000 right now. The US also hosts the tallest mass timber building in the world, the world record right now, which is the 27-story Ascent building in Milwaukee. So people want to see this. And then the third reason, directly connected to the work done by UC Canterbury, is that although the 2,000 buildings that I showed you earlier, most of them using a concrete core or steel brace frame, there's an opportunity to grab what Canterbury did, post-tension the timber system, put them in a rocking wall. I know there's two passes. The one is post-tension the frame, one is raw wall. We choose to go with the wood, and then see how it works out. We put everything together. In fact, even before we did the test, the design engineers on the West Coast, this is specific from Lever Architecture and KPFF, they did a fully permitted 12-story building called Framework. Some of you know that. It was not built only because of financial reasons. I believe at the last moment the developer pulled the plug because there's one like affordable housing incentive goes out, then they're gonna lose like $1 million if they build this, so they didn't do it. But post-tension rocking wall at this height, at this scale, has never been validated and tested in real earthquakes. So that is the purpose of this project. So basically, we are under the umbrella of trying to find a way to build almost earthquake-proof buildings, tall wood, and using mass timber rocking wall. The project started from archetype discussion, where we look at what type of building will actually sell, in the U.S. market. It turns out to be, gravity framing plus some sort of core. So we did some small tests. Some of you might see me present this 2-story a couple of years ago. Then today we're going to talk about the 10-story. The building, it is built based on a above code. The U.S. current code is similar to New Zealand. But we're gonna go for above code. We look at no damage to structural system under design level earthquakes, repairable damage under MCE, but there should not be any residual drift. For non-structural system, that's a little bit loose. You can get damaged. So that is what we're shooting for. Just a spoiler alert. Later we found out that those performance, even they are set this high, they are actually exceeded. So the building itself, if you look at the plan view, we're limited by the shake table. A shake table is the yellow here. So we have to put our gravity system on the shake table. Then to increase the floor size, we actually extend it out with patios. There's two pair of rocking walls. On this direction, with the X direction, we have the CLT rocking wall. And the Y direction, we have the MPP mass plywood rocking wall. The elevation of the building reveals that it is total of about 35 meters. It is the world's tallest full-scale building ever tested on the shake table. Building material, I have to, looking for donations everywhere. So Frivers give us the rocking wall on the Y direction. SmartLam provided rocking wall on the X direction. Then the floors, it's from everywhere. We get the floor from Europe, from Mass Timber Services. That's a Canadian company. CLT, GLT, then NLT and DLT from Structure Craft. And finally, there's a new product from Boise Cascade called a veneer laminated timber, which is basically plywood on steroid. They not only did all the top 4 floors, they also used their LVL. We did all the columns and beams because glulam is expensive and donation is really hard to find. But yeah, Boise Cascade, their LVLs are great. Then of course, our old friend Simpson Strong Tie did all the hardware. The rocking wall itself, as you can see in this picture, it's coming in 3 panels. Why? Because yeah, it is very hard to ship, if not even impossible to ship a 110 feet tall long panel or 35-meter panel. So they came in 3 pieces. We put them, we connect them in the middle, and then it's a rigid connection. So the entire wall is one piece. It's a 1 panel rocking wall with a 35-meter steel PT threaded rods. The system is actually quite simple. The construction of building itself, the gravity system apparently is just like any typical construction. You get a stair tower where we get donation from a modular stair tower company, Construction Specialty, and Timberlab and Swinerton did the construction, which is the most exciting part is actually try to stitch the wall panels together in mid-air. The construction took about 5 months, but there's one and a half months we're waiting for parts. You're like, okay, waiting for what part? Okay, well, let me tell you a story. I wish I could tell you that everything went great. There's no hiccups. Everything just perfect. No, this is probably one of the biggest challenges during the construction, where the walls are connected with the epoxy rods, which means you drill the wall on this side and on the other side, then the holes should match. Then you put a steel threaded rod in there, and then you inject epoxy. But the issue comes when the fabricator, which is another fabricator, it's not Timberlab. Timberlab did perfect job, but we outsourced this part of fabrication to another fabricator. They did a hand fabrication, and the holes didn't match up. Then what are the solutions? Because the panels are donated, I can't get another panel. So we have to actually fabricate those steel couplers. Those are steel plates that are 4 inches thick. 4 inches, what is that? It's like 110 millimeters. We have to drill the holes, although you look at, oh, those 2 panels are the same, but no, everything is actually mapped to the real as-built wood. Then we drill each one of them individually. And then the plastic, you see what that is? That is the one we use to kind of capture the whole location and put it in a computer model, and then have the shops, CNC, everything. Then you put, this coupler allows you to still use epoxy rods, but you can epoxy the coupler onto the wall on each side, and then bolt it on the other side. So, like I said, 1.5 months and $200,000 later, you got this connection, which actually works perfect because if you plan it ahead, this is actually a valid connection detail. You can do it in normal life, and probably won't cost that much, because if you plan it ahead, it will be much easier. And then we also tested the epoxy rod connection because, force-wise, it is epoxy rods. You can also see some like center shear rods. We didn't do that with the coupler is because those are short. The tension rods are much longer, and we for the shorter rods for shear, we just enlarge the holes. So this give you a kind of good picture of the size of the building, and also this is towards the end of structural construction. That is actually the final roof panel. In fact, you don't see it here. We actually have our signature on the back side of it. Everybody's. So once that puts on, the structural system is complete. If you've ever been to San Diego, maybe you recognize the area. This is a Miramar Air Force Base area. You see, it's actually a kind of outside of skirt of San Diego, and then you will see the oceans on the other side. You see the cities. The red tower, the 2 red tower you see here are the safety towers for the shake table facility. Those are put in just in case if you want to test like a 6-story or 5-story building, you try to collapse into the wide building. The wide building is actually where the hydraulics are, so they don't want that. But yeah, our building is just too high. They figure they have a 6-story safety tower, it should be enough, but yeah. I think later testing 10-story building will become a norm at UCSD. That is just a non-structural system. We also are testing non-structural system. It is important because the resiliency of the building, we're looking at no damage systems. It doesn't help too much if all your windows are broken and all that. So we want to test different non-structural systems. On the facade side, we have 4 different facades. As you can see, it's listed here. Most of them are light cold form steel, typical building facade. We have interior walls as well. Then we have apparently stairs. Those are some interior wall detail, and then there's some stairs. They all have flexible joints, because later you're gonna see them working when I show a video. And the structural system on the gravity side, Simpson Strong-Tie really designed some very flexible joints that can endure repetitive earthquake attack, like thousands of cycles without getting damaged. The key, as you can see here, is to allow it to rotate. The stairs the same. We have 10 stories, so our stair manufacturer, construction specialty, they are able to test different systems, from very simple system like just a slotted hole to very elaborate system of their 3D drift compatible connections. The instrumentation of this building is also, I think, the first in the history, a building that's instrumented with over 700 channels of data, and all the sensors, accelerometers, displacement gauges, load cells, string gauges, tilt meters for rotation. Yeah, it's a lot of work. It took us about 3 months to get it all ready. And when everything gets installed, you need to get plugged into the data acquisition system on site, which has about 750 capacity. We almost use all of it. And yeah, a lot of people ask why you don't use wireless. For a dynamic test where time syncing is critical, and you have such a density of sensors with a lot of interference with steel and building, yeah, the wired is still the only reliable way to do it. Yep, another view. This is how you plug in 700 sensors. So we also did some pretty cool, what do you say, LiDAR? Okay, yeah, point cloud. So basically, there's a group at UC San Diego. They have drones, they have LiDAR. They just came in and did a data preservation for the building before we tested, and after we tested, they have point cloud models. So the building apparently now is all gone, deconstructed. But if I want to know if I really punched that nail in that connection, I can go back to the point cloud model and see it. Not that I want to, but yeah, then now a lot of people ask, okay, are you gonna collapse it? No, the answer is apparently no. First of all, the UCSC site, they will not allow us to do it. Second of all, this building was designed for a specific location. It's actually in downtown Seattle. And then we want to test what we want to test is not just the building, but the design methodology. So we want to test it to the design hazard levels. And then the question is that how many tests you're gonna run. Initially, I was thinking we're gonna run about 20 tests, because I've done 2-story tests before. That one we run 14. But as we actually start testing this thing, that's why I say it blow our expectations. It just won't get damaged. So we say, okay, well, we can collect more data. So we just keep running. And in phase 1, we run 88 earthquakes. Around that, about half of it is at or beyond the design level earthquakes. There's no repair in between that were done, and we even run 3 MC earthquakes without any repair. And you can see the different direction we run, the PGA, and hazard level, as well as the source type, because Seattle, you could get different earthquake source types. So without further ado, I'm just gonna show you a video. This is the largest 3D shake of MC Loma Prieta, which is scaled up. And then you see a drone view on the top of the building, and you see a close-up on one of the rocking walls, and you see the entire building. Okay, I think because of the internet bandwidth, you don't see them sync quite well, but I mean, you got the idea. You see a lot of higher mode effect on the tall building. The closing up, I mean, we have a lot of cameras on the inside too. This is another earthquake, which is the Japanese Tohoku earthquake, which is very long. It lasted for 3 minutes. And then I'm just showing you the strong motion of lasts about 1 minute. You can see these are from the interior wall. And for this one, you look at the top, that's where the sliding track is. For the stairs, you look at the landing, that's a flexible joint. And then for this one, that's a facade. It's a facade on the corner of the building because, yeah, the corner, we have some flexible joints to enable the corner to move. You can see the sliding track here. On the corner, yeah. And then the joint right here. Yeah, the thing about those Japanese earthquakes is that they last a long time. In fact, in Tohoku earthquake, the high skyscrapers in Tokyo keep vibrating for about 5 minutes. I want to show it to the end because this is a clear indication that the building recentered because the non-structural system returned to their original position. And you know that non-structural systems themselves cannot pull themselves back, so the building must be recentering. What I showed you, the Tohoku earthquake, it is so long so that the shake tape only have the capacity to run it in 1D. But what about 3D, right? This corner is important. We look at it in 3D. This is a 3D Loma Prieta earthquake, the one you just saw. And now you can see it's a higher mode response where there are a lot of fast movement. Then after at the end of the earthquake, you get the first mode response. Right now, you can see that it's a slower movement with huge deformations. But you know, after all is said and done, remember this is 3D motion. The non-structural system will end up at exactly where they started. That proves that the building can recenter. So is there any damage? Yes, we see some non-structural damage, but structurally we did the very detailed inspection. There's no detectable damage. Even after a lot of tests, we pull the rocking wall out and we look at the bottom toe, the corner of the rocking wall where it's supposed to get crushed. You only see a little bit of that. But because there is some damage to non-structural system, you did see building soften up. So the natural period, if you look at its first mode, going from below 2 seconds to above 2 seconds, about 1.7 to about 2 seconds in each direction. Then the building overall, the performance is great. If you look at the industry drift, at the MCE we're about 2%, which is exactly what we predicted to be. The acceleration, you reach about 2G, but that's MCE. If you look at the design level, it's about 1.3-ish. One interesting thing, this is a clear indication of higher mode effect, is that the maximum industry drift and maximum acceleration, they don't happen at the bottom of the building. And they also don't happen at the very, very top. They happen around this upper part. Acceleration is even more interesting. The maximum acceleration happens at the middle of the building and then tip of the building. That is a classic sine wave higher mode effect. This is another, I talk about the non-structural system, right? I might have to show this one. We're trying to break a window, but we can't. The reason is what you just saw. This piece of glass is likely the heaviest piece that is on the curtain wall on the northwest side of the building. This piece of glass is a 2-hour fire-rated glass from Germany. The glass itself is about, let me see, about half a ton, I think, 2 kips. Yeah, 2 kips, half a ton, is that right? Okay, anyway, it's about 200,000 pounds. Not 200, 2,000 pounds. But what happened is that the glass just racking the frame, because now the modern window manufacturer, they basically, to account for thermal expansion, they have built in some flexibility in between the frame and the glasses, so that although not specific for seismic, it actually worked pretty well. This is another view for a design level earthquake to show you how would it actually feel if you're on the 10th floor of the building during a design level earthquake. This is Chichi earthquake 3D. We have our decoration there. Some of you might remember a test done by Professors Siccardi, Ario Siccardi from Italy many years ago at eDefense, where a rigidly built CLT building, it's a panelized CLT building, it recorded very high acceleration on the top. But for this one, as you can see, you see the rocking wall moving, you see the gravity frame racking, you see the stair move around, but if you're there, your water bottle falls off. And then do you see the carpet? I intentionally put the carpet on because the carpet really ties the room together. So what do we find? Okay, there's higher modes, and especially the higher modes are very prevalent, and you see them at the beginning of earthquake when there's a lot of higher mode input. So if you look at our data, where you plot the building deformation shape and then hysteresis, before like T1, which is the beginning of earthquake, you see a lot of spikes. And then this picture, number D, is the uplift at the bottom of the rocking wall. So rocking wall is not rocking, it's not uplifting. And then basically the building are participating in earthquake in higher mode using just the elastic deformation of the rocking wall panel. Then after T2, when the earthquake slows down, then really the rocking starts, your hysteresis begins to smooth out. And then finally, you are reaching a first mode shape. But higher mode effect, I would say it's kind of double-edged sword. You have to account for it and then for overstrength. But once you take care of that, the higher mode is actually good for stability because it doesn't produce too much displacement. Then we have some very key knowledge now, truly major knowledge about what our post-tension force is. This is normalized by the yielding. So we started with about 0.4, 40% of yielding. Then during the MCE test, it goes up to about 55%. So not much because our rods are very long. Then for base shear, we normalize it with the building weight. So you can see there's in the US it's called the CS base shear factor, less than 0.3, even for MCE. For design, it's like right here, about like 0.17-ish average. Then also, because we can test this building many times, we are able to actually look at something that we always take for granted. We design the building decoupled in each direction, although earthquake is 3D. But if you really run the same earthquake uniaxial, biaxial, and triaxial, and compare the response in one direction, does it differ that much? The answer is actually no. The displacement doesn't differ that much. The demand doesn't differ that much. So we kind of validated that with the full scale test that what we've always been doing in our design is actually right. Yeah, go figure. More detail about the results you can find in a paper that's about to come out. I actually elect to have this paper to be open access. So once it came out, just follow my Twitter. I will give the link right there. Yeah, my Twitter is, I'll give you later. So after our test that we just showed you, 88 test, we did another 19 test. There's a researcher from MTU who did some dampers on one side of the wall. Then the Japanese collaborator coming in, Sumitomo Forestry, they did their own wall design. They ran another 51 test, including a lot of very large earthquake from Japan, which the paper is coming out, but yeah, right now I'm under NDA, so I can't talk too much. Then we take the top 4-story off. Then it became the 6-story building. We hand it over to our collaborator at Oregon State University. They did another 86 test. So yeah, if you look at the gravity system, because lateral system we switch them back and forth, but gravity system on the bottom 6-story, 244 earthquakes. Yeah, it's likely the world's most shaken full-scale building, but there's no structural damage. There's no residual drift. So like Danielle said, yeah, I appreciate that. It is almost an earthquake-proof building. So what is the main takeaway? The earthquake-resilient building is not only possible, but also practical, because we did it with some normal contractor on the market. There's nothing too special about it. The post-tension rocking wall, I believe that's a key, and it is replicable. And you just need to be careful when you stitch panels together. It'll cost you if you don't do it right. The gravity system designed by my collaborator at Simpson Strong Tie is really great. I think I have to speak to that, because if a gravity system collapses, it doesn't matter how good your rocking wall is. Finally, the non-structural system, if you detail and design it right, it can be functional and repairable, even at MCE event. Right now, we are doing the codification through the FEMA P695 procedure. This was led by myself and my collaborator, Ray Zimmerman, who's, yeah, I have to say this, he's probably the one of the top timber engineers right now in the US. So we're shooting for ASC 7. The next update cycle is 2028, but we will actually have to do all our work by next year. So you'll see some reports coming out. So with that, I think I concluded my presentation. And like I promised, here's my Twitter. Just go check it out. In fact, I started my Twitter when I started this project. So if you just check my Twitter, the history, it'll show you how the building was built. There's a lot of good footages I cannot include here. And then apparently I'm gonna give a loud shout out to our sponsor, especially National Science Foundation and the US Forest Service. Without them, this could never be done. And also this is a combined effort for all the wood industry in the US for the most part. So with that, thank you. And now I'll start to take some questions.
Thank you, Shiling. It's always very impressive to see shake table tests of those buildings, and not just the theory, but also the application on a shake table test. So we have some questions, and please people send them through on the Q&A pen. Shiling, one of the questions we got was someone asked about the presentation itself. Well, this video is being recorded and it's going to be accessible on the Timber Design Society homepage, and it's going to be hard to share the presentation with the videos. So I encourage you to get in touch with Shiling directly via his email address, and then that can be sorted out on that end. Technical questions, Shiling. Someone is asking if you have done numerical time history analysis and how the results of the shake table tests and the numerical ones matched.
Yes, yes, we have done that. It'd be crazy not to do that. So there are two main numerical models developed. One is the OpenSys research focus model developed by Sarah Wichman and Jeff Berman at the University of Washington. That one matches pretty well, actually very well. Then we have another one developed, I believe, by Simpson Strong-Tie, Steve Pryor. He's a R&D lead there. He developed a SAP 2000 model, and it works also very good. The reason I tell you why it is work good, because although at impressive scale and testing and all that, this is a very simple system. In fact, this is I would say the most simple wood lateral system I've ever studied, because I used to study light frame wood shear walls. You have 500 nails per panel. But this one, you have very limited connections. The mechanism are very simple. You can actually do hand calculation. So there's no surprising that those numerical models work. But yeah, they did spend a lot of time trying to look at the crushing of the wood at the corner. But once that is figured out, the modeling is not that difficult. And it matches pretty well. And also the numerical model paper is coming out soon. Okay, probably towards the end of this summer.
Perfect. So related to what you just said, the timber crushing, someone is asking if there was any reduced stiffness in the subsequent tests. I mean, you must have had some sort of damage. Did it affect the building behavior somehow?
Yeah, I showed a slide where we see the elongation of the building natural period when we run white noise test. So the initial stiffness did decrease, but overall performance, like what we intended to be, so which means in large earthquakes it recenter, and also without having more damage, I think that is also true. Which when the walls start rocking, the mechanism, those parts they are preserved pretty well. We didn't the damage didn't do that. So yeah, there's some damage that affect the ambient vibration frequency, but there's no damage with regard to the intended functionality of the building and lateral system during a real earthquake.
And that speaks for the system itself, which is really a really good outcome, I would say. Obviously, you had some issues with the epoxy rod system in your specific scenario, but what are your general thoughts? Could the epoxy rods be omitted with like continuous rod systems or embedded over the full height or other systems?
I mean, if you want to embed it somehow, I mean, full height, that'd be a tall order, because you see the panels are shipped on site separately. How do you embed? Yeah, we have trouble embed a rod that's about 2 meters long, and then how do you do the full height on site? The key is on site. I mean, you have to assemble those things on site. If you can find a way to do them on the externally, yes. I think to answer the question, if you can do it efficiently and then cost effectively, yes. I think that's a good way. But it's hard. Or another option is that you actually install the rods on each wall panel before you ship them, and then when you come to site, then you just connect the rods. That's another possibility. But those type of things mechanically can all be done. Practically, you need to think about the economic of things and constructability.
Yeah, I fully agree with your comment on this one. And actually good that even though you are doing a test building, you still had to think about the cost and reality of what's constructible and whatnot.
Yeah, the cost is all I think about. Believe me, Daniel. When I'm on site, I don't think about technical stuff.
Right. There was a comment about the facade system and the movement detailing on this one. Is there any work on non-structural elements which one of your team members is gonna work on and publish something?
Yeah, yeah, of course. I didn't do that. That owner belongs to my co-PI, Professor Ryan at University of Nevada, Reno. In fact, as we speak, his student just submitted a paper. Just submitted, right? Still have to review, but I think that's going to come out later this year. On the facade that we talked about, they have a detailed design details and demands and performances in that paper too.
Mhm. It's good. I really appreciate that you cover so many aspects in one building, but it makes sense. You don't have the opportunity to test a building that big that
Yeah, I
often.
mean it's a once in a lifetime opportunity. So everybody, yeah, also I appreciate our sponsors to donate all those things. Yeah.
Someone is asking about how you accounted for the additional live load on the building itself.
Mm, yeah, you see some of the earthquake shake table tests, they have added mass and all that. For this building, you don't see any of that. The reason is when we built the building, we came up with two choices. Because the building as is without any added mass, the natural period is almost pushing 2 seconds in our numerical model and in our ambient test. So if we really added more mass to be like, okay, per square footage real, the building will have a natural period of like 4 seconds, which is not dynamically representative of a 10-story mass timber building that we want to test. So we have the choice of either match the natural period or match the quota floor mass. We choose to match the natural period because we view that as more important on the dynamic analysis of the natural system. And I would assume that if you know anything about structural dynamics and design, you will agree with our decision.
Thank you. There's a question about energy dissipation. So the question is, where did the majority of the energy end up, and was there any intentional areas of energy dissipation in the structure, or did you purely rely on the change of stiffness and therefore the ductility out of the rocking and gap opening?
The energy dissipator are the UFPs, U-shaped steel flexure steel plates. Yeah, you can see them here. You see that, right? So there are U-shaped steel flexure plates that are between the rocking wall and what we call bonding column. Then when the wall rocks, they will deform and dissipate energy because those are already yielded. And in our mass timber rocking wall design provision we developed, if you're interested, you can look at this paper. It's already published. We kind of copied what the concrete rocking wall folks demanded. At least 25% of your strength of your rocking moment strength has to come from yieldable elements. So that is where the energy dissipation is. What is not accounted for is when you rock, then there's pounding. That there's some energy dissipation there. Also fraction of the non-structural system. Those are inherent energy dissipation. It's very hard to model in a numerical model, but so we basically replace it with really damping during our simulation. You add 1 or 2%, and that's it.
Yeah, that's a very clear answer. Thank you. Based on the UFPs and connections, can you confirm that none of those connection plates and fixings or UFPs actually have been replaced during the testing? Probably related to the damage question from earlier.
Yes, I can confirm that. We see we see them deform. We can look at the, you see some of the yielding patterns they change, but there are no fracture throughout all 88 tests. In fact, we have pre-made some. We have about like 10 extra, but we never end up using them. So that's another couple $100 wasted. So.
So you also didn't encounter any low cycle fatigue, failures, like considering the repetitive deformations they went through?
No, in fact, yeah, we didn't see any in this test. That is true. And in fact, even the subsequent test, like done by Andre Barbosa, they didn't see much. I think what helped really is, in my opinion, I don't have solid data for it, is when you do a lab test on those U-shaped plates, you fix them into a testing gig and you just do this, then they fail. But your connections are very, very, very rigid, because when you're doing a test, you don't want to see any slip here. But when you're in a wood building, although we have tried to do that connection very rigid, in fact, we did test in Japan to make it rigid, there's still a little bit of movement. So the wood is just, if you want to have the wood to force the steel to like fracture, it's hard to do.
Yeah. And that's a really good segue, Shiling, onto the last question, which is about the floor to rocking wall connections, which they always seem to be a bit of a headache in design, but in your test, they don't show any significant damage and problem. And I'm also curious because I did work on it doing my PhD work, and my conclusion was exactly what you just said. The timber is flexible enough and the connection is flexible enough to take care of it, but obviously more than happy to hear your view based on the testing you've carried out on that.
Yeah, so I'm gonna show you the connection, what it looked like. The connection looks like this. So basically, the walls are not connected to the diaphragm in any point except for here and here. Those two, they don't transfer shear. Those two are the outer plane bracing. So the only shear transfer is this mechanism where you can see we have collectors on the floor. We collect all the shear and get it into this steel bar. We call it a shear key. Then we insert it into the rocking wall inside a slotted hole, where the side of the bar, you can see a little bit white here. They're on Teflon type of friction-free surface. Then the side of the bar is actually a little bit curved. So when the wall rocks, your vertical motion of the wall and lateral motion in respect to the diaphragm are decoupled. So basically, the diaphragm will not be pushed up or down when the wall rocks. It'll just be dragged sideways. And I visited, Daniel, I visited your office, of course, and you guys have a different detail relaying just simple bolts based on wood flexibility. We actually were thinking about doing that because it's cheaper, apparently. But consider the amount of earthquake we have to go through, like 200, we don't want it to get any damage. Mm-hmm. So we elected to use this, we call it slotted shear key transfer. This has the advantage of being resilient, simple to analysis and everything, but the disadvantage is that the rocking wall became a pure lateral system. It's not a gravity system, mm-hmm. because there's no gravity load on the rocking wall.
And did the Teflon plate work as intended? So was the diaphragm remaining mostly at the same plane, or did it still move a little bit with the rocking walls?
They move with rocking wall, but they are stay in the plane. So yeah, I don't think they kind of rotate or anything. Yeah, the gravity frame is also, you can think of them as pin. Yeah. So yeah, there's no significant out of plane rotational movement of the diaphragm. Diaphragm also, our diaphragm, because it's quite small, I didn't really touch on that. No damage whatsoever. If you have a larger diaphragm, you have to be a little bit more careful. But for our test, it's a rigid plate.
I was about to close up, but there's another question came in. Did any penetrations to the rocking walls or floors get accounted in your design, in your testing? Excuse me.
Let me see. Did any penetration rocking wall get accounted for testing? Yeah, I mean, we have apparently through the rocking wall or floor, not through the rocking wall. Rocking wall, they are fixed. Rocking wall, they're not penetratable. It's a whole entire piece. The floor, you do have a penetration right here, right? And then if you don't have a stairway, you could do a small penetration just around the rocking wall, which I did do that test 5 years ago, or 6 years ago. in a two-story test where we just penetrated the floor with just a little slot, which is fine. In fact, it is even more beneficial because now you don't need that complicated bracing system. Now you can just brace it with some compressing only brace on both sides. In this test, because our rocking walls are all on the outside, like this bracing has to take both tension and compression, so that looks a little chunky. If your wall are actually slotted in, then your bracing will be much easier and cost effective.
Great. Shiling, I have a last question, which is my own question. So you've done all this amazing testing, shake table tests. Now, obviously, there's a bit of numerical and follow-up work and design standards work. But what's next in your timber research moving forward? Like, what's the next big project you're gonna work at if you are willing or able to share that with us?
I think right now I'm doing the codification, but you can see that's actually part of this project. And I need to do some traveling and try to learn from other experts around the world. But I think once I get back to the US, I'll start to think about my next proposal. I would like to see. I really want to do something that's gonna impact the practice and industry. Maybe something related to easy assemble the mass timber systems on site, or maybe I'll go with wind, because the United States, right? There's a lot of tornadoes and hurricanes, and there's some need there. I don't know. Yeah, it's a tall order to have me come up with another idea like this in the short term, but I'll keep trying. I'll keep
Perfect.
everybody posted. Yeah, just follow my Twitter. Okay, follow my Twitter. I'll keep
Yes,
everybody posted.
I'm enjoying your Twitter account, and I'm definitely looking forward to what's next. Thank you so
yeah.
much. Yeah, thanks for that. So thank you so much for sharing your knowledge, the testing, your thoughts. Really looking forward, and great to have this connection. And let's keep the connection between you and New Zealand alive moving forward. So thank you very much, and thanks to all the attendees, and looking forward to the next TDS webinar in a month's time.
Yeah,
Thank you
thank you,
very
Dan.
much.
I'll definitely come visit during your summer.
It's gonna be a different country.
Okay.
Thank you very much. Bye-bye.
Bye.